Hoy tenemos el placer de contar, igual que ayer, con Ryan. Hoy será su presentación. Ryan es un arquitecto por la Universidad de Aarhus. Está especializado en diseño robótico y diseño computacional. Y su especialidad, bueno, ahora mismo está haciendo un doctorado en colaboración con Zaha Hadid Architects, y también ha trabajado un poco con la ETH de Zúrich, haciendo sobre todo modelado complejo de shells, de burbujas, y hoy nos mostrará un poco de su trabajo. Para mí es un placer introducirle, así que bueno, encantado de tenerte aquí.
Yeah, thank you for the nice introduction, Vishal, and thanks for the invitation to Vishal and Farhan to come to this fantastic lab and to speak to you all today. When Vishal told me about the fact that they're opening a new lab here at the school, I thought that it was appropriate to speak about computational fabrication as opposed to robotic fabrication, because in a world like this where you have a fab lab and you have a lot of different machinery, the concepts are not specifically tied to robotic fabrication, but actually it's kind of it's a system that's just driven by computation. And this is kind of quite closely tied to the idea for me of innovation in terms of architectural practice. So architects are kind of natural-born innovators in a way. When we design, we're always looking for new solutions and new ways of doing things, changing the status quo. And I believe that these sort of tools enable us to go beyond designing specific objects and actually be innovative in terms of processes and things that we offer to the market. So I'll kind of unravel some of these things. And then I'll show a few projects that we did at a lab similar to this in Denmark. So maybe to show a little bit of the world that's possible with some of these machines. I studied in Denmark. I was part of a unit, the master's program at the Aarhus school, that focused on digital technologies and architecture. So we were one of the first groups in the school to tackle some of these things. And throughout my thesis project, I worked with building simulation and computational design and robotic fabrication, and how we could integrate these three different things. When I finished my thesis, they asked me to stay and to found the lab at the school. So we went through a similar process. They had just bought some equipment, and then we had to design a teaching program and a research agenda around some of this equipment. Shortly after that, I joined Rock Architects in Zurich to help on a project which was tied to the block research group, the Nest high-low roof, which is a very, very thin concrete shell. So I had a little bit of experience with some shell structures, but this kind of exposed me to the really the innovation that's happening there at the moment. Last year, I joined CF Muller Architects, where I'm leading the computational design group. And we work a lot with sustainability engineering and complex modeling for the whole office. So we do a lot of daylight modeling, a lot of life cycle analysis, and then some work with facades. And just recently I joined the Aarhus School of Architecture again to start a research project in collaboration with the computational design group at Zaha Hadid Architects and a company in Denmark called Odico Formwork Robotics. And the project is focusing around just-in-time fabrication of mass customized timber housing. So quite a wide portfolio. But one of the projects that I've also started in the last year is a consultancy called Axis, which is also the same name of a robot programming plugin for Grasshopper. And so the idea was that Axis would become a little bit of a platform for innovation to do some consulting work with firms in terms of how we can manufacture things and how we can design things in a more intelligent way. It's also a bit of a teaching platform, so we do a lot of workshops, we try and post tutorials, and we're working on a few other things right now. But it's basically about providing innovative digital solutions for the building industry. We're a team of designers, like first and foremost. Like to think of ourselves as innovators and question the way that things are done. And we're developers, so we have technical know-how to actually implement these things. So in this order, we see that we can kind of come up with innovative ways of designing, we can challenge the way things are done, and then we can provide the solutions to help others to do it. We focus on geometry, simulation work, and fabrication, mostly robotic fabrication. So I'd like to talk a little bit about innovation, and my understanding of it is that it's to introduce changes and new ideas in the way that something is made. So often this term is kind of reserved for the digital avant-garde, the very, very high-end complex projects that we see as architects. But actually we innovate in every day. Everything we do is innovative. We've also kind of got quite well acquainted with personal technological change, but I believe that the change is just about to happen in our industry. So obviously there's a lot of talk about building information modeling, but actually the potential to touch the way that we actually make our environment, this is truly revolutionary. And this is just about starting now. To put in perspective, the estimated size of the global construction market in 2025 is $12.7 trillion. So like that's a big number, no matter how you look at it. And actually other people in other industries are starting to notice this. The way that a lot of people look at it is that even if you can secure a tiny fraction of this market, you're talking huge numbers. So software developers, global technology corporations, municipalities, cities, they're all getting on board with the way that we design and we make our cities. So everybody's fighting a little bit for the piece of the pie. But I think that we're excellent innovators. So we have a chance to actually be at the forefront of this. So this is a huge market, and we're basically trained all the time through buildings, concepts, design to innovate and question the way things are done. This is mostly, how do you say? This is not only about the building design, but now I think the potential is really in the process design. Industrial robots, they're interesting for me because they're the key to designing entire processes. They go beyond specific objects, but actually to design processes at a large scale that allow us to question the way things are done. The definition of a robot, you're familiar with them from this workshop, and that's kind of what we're here to do this week, is to introduce everybody to it. But they're automatically controlled, reprogrammable, and multi-purpose machines. So the basic idea is that you can make these things do different things every time with different processes, and you can adapt them to what you would like to do. We're interested in them. They're particularly cheap. I mean, they're not the cheapest things in the world, but compared to other machinery, it's actually quite accessible to get a second-hand robot. And that's why there's been a huge surge in the amount of startup companies doing 3D printing, robotic manufacturing in timber and concrete and steel and so on. They're precise enough, so they're ideal for building scale because 1 or 2 millimeters for us is maybe acceptable. In the manufacturing industry, this is not really okay. So what you'll find is that there's a lot of these machines that have just a tiny little bit of inaccuracy, and you can pick them up for a very, very good price. They also allow you to work at a scale that's very suitable to architecture. So while you have a 3D printer or you have a CNC machine that's a little bit limited in what you can do, as soon as you have a large robot like this, you can really, really talk about architectural scale components. Even buildings, you can have the robots autonomous. We're interested mostly because academically speaking, they allow you to do a huge variety of different things. So I will try and show you a little bit about some of the things that we've done in Aarhus and spur the imagination a little bit. They're often referred to as an armor without a hand. So the manufacturers, they deliver these machines and they really don't care what's on the end of it. Their job is to make a machine that moves very precisely in space and allow you to design whatever happens on the end out. An ideal platform for innovation. I also like this quote by Esker Dijkstra, the computer scientist, that the simplicity is a prerequisite for reliability. And this is true, I think, of the robots. They're very, very simple machines. I think through the workshop you might see just how simple they are and approachable, but it actually allows you to build very, very reliable processes. Because of all of these reasons, the accessibility, the ability to work at a large scale, and the ability to be reprogrammable for different purposes, there's been a huge surge, as I mentioned, since 2006, 2008, in people buying these machines. And one of the key stakeholders in the game in terms of architecture is the Association for Robots in Architecture. This is a global organization headed by a few people based in Europe. And it's also a platform for knowledge creation and knowledge sharing. And they host a conference every 2 years called ROBARC, Robots in Architecture. That's where all of the cutting edge research is happening in the field. Okay, so I think in the context of that this is a workshop-based presentation, I will just describe a little bit how robots actually work. Effectively, you have 6 different axes and a tool at the end. The traditional way to program them is that you move the robot from one position to another, you save that point, and you move it to the next one, and you save that, and then you can just press play, and it will just repeat it over and over and over again. If you map that out, what you kind of see is that you invest a lot of time, and things become very, very inflexible as you start to invest more time in the program. So if you build up something that's very complex, as soon as you need to make a change, you actually have to kind of change the whole thing. Or if you would want to do something completely different, you have to invest a lot of time again. The advent, or let's say the advantage that we have as architects is that we're actually quite used to doing things parametrically. When we model something, we start to have building systems, software packages where we're used to having very, very complex designs, very complex geometry, and having to update it all of a sudden. So using some of the capabilities that we have with Rhino Grasshopper, we can build on top of that and use that for robot programming. So when we parametrically program the robots, what you see is we do something a little bit similar to this. So we set up a program, we try it, we test it, we make some changes, we go back and forth over and over again. This means that when things get very complex near the end, we actually have to make less and less changes because we've been doing it all the way along. To show one little example of how that might work, this is a 3D concrete printing example where we just move from frame to frame. We pick a point, we see how the robot is going to behave. We move to the next point, we check the same thing. If we would move too far away, you can see from the robot over here that eventually you kind of run out of space. Then we get a warning graphically in our CAD program. Similarly, if we would hit something, we get a warning. And ultimately, we kind of go through the program, we simulate it. So this way of staying in our digital CAD models and testing how things are going to be fabricated allows us to, with a high degree of security, check how the manufacturing of the piece is going to go. Okay. There it is. I'll just describe quickly the process of working with it a little more. So the first thing is that we always create a digital twin. So we have a digital model of anything physical that we've set up. Next thing, we generate the tool paths in our CAD program. So we take our geometry and we create the path at which the robot is going to move along. We simulate it and correct it, and then we export it to the robot. And we can actually close this loop again. We can go to the next piece, and all of the same steps that worked for the last piece, we just apply them to the next one and update it. In Aarhus, we bought some small robots and a large robot, and I'll show a few projects from either or. Because we bought ABB robots, we had to design our own parametric robot programming toolkit. It's called Axis Robot Control, and you can download it from axisarc.tech. It's basically for the control of ABB and KUKA robots. We can do offline and online programming. And the reason that we needed to make our own tools was because at a certain point, the architecture school in Aarhus, they bought a lot of equipment, but they started with CNC equipment and they started to kind of add on top of that in terms of the robotic technology. So people were quite well acquainted with using these CAD/CAM software packages, but we didn't have anything for the robots. Coupled with that, we have a school that's based on a strong tradition of craft. So materiality is very, very important. And people have all of this implicit knowledge about how materials will behave and how different geometries are suited for one thing and the other. But we wanted to create a platform for them to integrate it directly into their manufacturing processes. So we decided to build our own tool that was suited to these projects specifically. We started off with some very, very simple exercises. So we were quite interested in things like how the robot could potentially help people to draw. So we attached some pens and different things to the robot. We did some light painting, which is something that we'll also do here at the workshop. So by simply attaching a little light to the end of the robot and moving it in 3D space, you take long exposure photographs, and you can start to create something that's kind of not digital or physical, it's something in between. And we also had a little bit of fun. So we had an iPad. We were moving the iPad through space, and then we were sectioning a Rhino model and trying to project things from the digital realm into the physical realm. But all of these were good exercises in terms of getting used to the robot, because all of these things are very, very low precision. Like, it doesn't really matter if the light is 1 millimeter or 2 millimeters higher at the end of the day. The thing is that people got used to going from a digital model and programming a robot and going back and forth and back and forth. We had some similar exercises where we worked with sand. Oh, maybe I said on something. Where we worked with expanded glass sand. This is an exercise that we did with Michael Knaus from ETH Zurich. The idea was that we would form inside these boxes. We had a metal form sitting underneath the sand, and the idea was the robot was just very, very softly moving the sand and allowing us to actually take these molds and put them in an oven, and then we would freeze them. So we could work with the material on a very, very fine level, and then eventually we could put them in the oven and freeze them. And these are actually ideal mold works for concrete, and you can see some of the projects that they've done where they've continued this a little bit. We experimented with 3D printing in ceramic and clay. This is a very, very interesting process for us because it's a very, very tight connection between the geometry and the material. There's certain things that you can and can't do. And it's to understand how to work this process particularly well, you have to actually get hands-on with the material. And that was really interesting for us as a teaching institution. One of the nice things about robotic processes is that you can take knowledge that you develop on a small scale and you can scale it up to a larger scale. So in the case of the 3D clay printing, what we did was we just had to buy a bigger extruder or build a bigger extruder, and all of a sudden things that are small objects can become building components. Like this was a column, formwork for a column. So we would print in clay and then put in reinforcement and then cast inside. Also working with the small robots, we developed an interest in timber fabrication. So again, with Michael Knaus from Zurich, then we were interested in how we could design and assemble small timber structures, basically. So we started with the small robots with little proxon, small little automatic saw, and the robot was picking it up, cutting the stick, and placing it in place. And this is kind of interesting because I'll come back to it in one of the projects that I will show. But it was the exact same process in principle to do it as an architectural model. We could take all of that knowledge and then we could actually build something at full scale. Another process that is particularly interesting for us was robotic hot wire cutting, which one of the researchers at the Aarhus school, Asbjørn Søndergaard, he went on to found Odico Robotics, which are now producing robotic hot wire formwork for some of the biggest projects in Europe and also in the Middle East. So the idea with this process was that we kind of flipped it around a little bit. We were interested in how the robot might actually fabricate the blocks and stack them together afterwards. But what we discovered was that it was actually probably more difficult to do it this way than it is the way that we're doing it at the workshop now. A lot of the processes that we developed, we we were more interested in how they were going to impact the materiality of what we were making, and not just ending up as a nice piece of foam at the end. So when we work in the Aarhus school, what we like to do is to always design some processes that come back to working with real materials: concrete, clay, steel, bricks. So what we did is we took the same process for the robotic hot wire cutting, and we had some exercises with the students where we would work with 30 by 30 tiles, where they were free to shape the formwork however they wanted. And then we would simply cast them and kind of break them over the next day. I have some more pictures of this later. But what's really interesting with this is that you can actually also start to play around with the texture of the concrete, because with different things that you put in on top of it, you can get different textures. So if you use fabric, or use plastic, or if you use some gel, this all changes dramatically the output that you get. EPS formwork is also very useful for forming timber, for forming plywood. So what you can do is you can robotically cut foam molds. Because foam is very, very good under compression, then you can apply like a uniform force, and you can pull plywood sheets in. And some of them, particularly the one on the right, had a very, very nice result. At the architecture school, I work quite closely with some of the researchers there. One of them is Anders Kruse, who just completed his PhD 1 year ago. And he worked with Wes McGee in Michigan. They were both interested in how you can use the steel bending technique that they developed in Michigan to robotically bend the formwork the reinforcement for concrete, because it's a very valid question that comes up when you deal with freeform concrete, is how do you actually reinforce it? So we had a shared digital model where we had some surfaces that we both had the exact same model of, and then they were doing the steel bending in Michigan and we were doing the robotic hot wire cutting, and they shipped it across and we just cast it in the lab in Aarhus. I think something that I've noticed with a lot of different processes is that they always leave some marks on the artifact, which is not to be kind of taken for granted. So when you robotically hot wire cut something, you're left with the very straight lines of the wire. If you CNC mill it, has a very, very different aesthetic, and it has a very, very different feel. So after experiencing a lot of these different processes, I now understand that it's not only about using the machines to make the geometry, but it's also about what sort of characteristics you would like to have. You can augment those, as I mentioned earlier, with the different treatments that they use. So these are some examples where we kind of took some of the technical knowledge we had, how to actually produce these forms using the robot, and maybe some of the material and just built up knowledge in the lab about how you can get different effects and different play on light with concrete when you use different materials. This was particularly interesting for a few people. So we went to South Korea to the Underground Gallery by Byung-Soo Cho Architects for the Architecture Expo in 2018. And we introduced this process basically to all of the Korean architects, because they had, I think in Korea it's like 90% of the concrete is done on site, in situ, and they always use formwork, but they always they build a very straight formwork and they dispose of it afterwards. So the idea of being able to do freeform architectural formwork was particularly interesting. So we set up a little factory in the gallery on the main street near the palace, and for 2 weeks we were just producing different forms and talking to people and trying to share them. And it's really, I think it's interesting because these sort of technologies, they're so mobile and they're so easy to move around. They can also be thought of as these like mini little factories. Okay, so it's a big long introduction into like lots of different processes. And now I'll show 2 projects in particular that relate a little bit more to what we're doing this week. One is a timber grid shell and the other one is a robotically hot wire cut grid shell. So this one was done in collaboration with Niels Martin Larsen and Tony Osterlund, both of And Nils is from Aarhus School of Architecture, and Tony is from a company called Geometria in Finland, who specialize in timber construction. And we had a site that was down in the old railroad tracks, I think it's called in English. Where basically it's a huge creative cultural area, so there's a lot of artists and photographers and architects sitting in these kind of buildings that they've reclaimed back. And it's a really interesting place to build some temporary structures. So for this we were interested in how we could cover a lot of space and how we could work with something that was lightweight but also sustainable. So we didn't want to use EPS foam, we didn't want to use anything that was very, very heavy, and we actually wanted to have something that we could potentially reuse the material again. And we looked around a little bit, some prior research and some historical documents, and we found this Zollinger lamella system, which is basically it's a way of putting timber elements together. It's in a reciprocal manner, so they all kind of support each other. And you can use very, very short timber elements, and you can span very large distances. Unfortunately, it ran out of mainstream use, because to get people to fabricate lots of very small pieces is actually very time-consuming and very expensive. But actually the robot is ideal for this, because you can shoot 200-300 pieces at a robot. They're all different, they're all very small, and it can handle them individually very well. So we wanted to look at if we could actually set up a process to do the same thing in our lab. We didn't have a whole lot of money to buy any expensive equipment, so what we did is we basically set up like a circular saw on a stick, which was really weird and looked a little bit dangerous, but it was okay. And then we also took a handheld router, and we just took all of the casing off it and just stuck it pointing up straight in the air. So we actually had hacked together a little bit of a system, and we were still able to fabricate these elements with, I think, like 0.35 of a millimeter of precision. So with very, very little means, you can actually set up a complex process to manufacture these things. There was a little bit of a logistical problem in if you make like 600 sticks that look almost identical but are not, then you have really a nightmare in terms of putting them together again. But we figured it out in the end. So these basically just click together, and the entire structure was just lifted into place. I think the entire structure only weighed 100 kilograms. I'm just going to let it play like this, because then we can skip forward through it a little bit. But we, it's tricky to see. So we had basically this form finding process where we relaxed the mesh that we had drawn on a plane, and we effectively created something that was that had minimal bending in the structure. So what we had is like a relatively uniform distribution of the stresses, and we had the locations for the joints for all of the pieces. So from this point and line model, which is similar to some of the tools that we're using this week, we were able to extract all of the cutting geometry, and we set up a little factory at the school where we had the students manufacture the raw material by just putting it through the plane. And then we pre-cut all of the timber elements to a specific size. So we tried to bin pack all of the elements into rough groups. So 1 meter, 1 meter 20, 1 meter 40, 2 meters. Okay. It's not being our friend today. Okay. Now we're back online. So we basically set up the robot to have this very, very simple gripper where we're picking up timber elements, then moving them over to a saw and cutting them manually. So it's a little bit similar to some other processes that are out there. Basically moving them through the spindle and cutting all of the joints out. I'm going to skip this one on a bit so we can see the structure going together. So again, with I think we were a group of 15, 20 students, and we had 1.5 weeks to do this workshop, and we were able to design together and analyze the site, design the structure, fabricate it, assemble it within all of the time. And I think it was something like 600 different pieces or something like that. And we just kind of like picked it up and lifted it into place. We had a very, very simple foundation system as well, just some concrete blocks that we had drilled some specific holes into with some metal connectors for the timber. So it's a very, very fun project. A slightly more complex version of this is what's happening at ETH. Well, a very more complex version of this is what's happening at the ETH Zurich at the moment with the Spatial Timber Assemblies project. They just finished one of their flagship projects, which was this defab house, where all of the wooden construction, all of the timber framing was cut and assembled by the robots in a similar fashion. So you have some circular saws cutting the ends, and then you just have screwed connections from the top. So there is the potential with this technology, the same models that work for small structures that you prototype in the lab. If you have bigger equipment and more precise machinery, you can build real scale buildings with this process. The other workshop is something that was done as the AA Visiting School, together with Tommaso Kusucci, who is a senior designer at Zaha Hadid Architects. And what we were interested in doing there was to look again at this robotic hot wire cutting process, to have the students get used to going back and forth between making and designing and informing their structure, and then to use those techniques to robotically manufacture the formwork for a concrete shell. And because we also did this one in like a week or just over a week, with also some tutorials in Kangaroo and in form finding and how to use the robot, we decided to manufacture the positive version of the shell from foam instead of keeping the negative formwork. So again, we use this robotic hot wire cutting process where you just heat a thin wire on a metal frame, and then you move it through expanded polystyrene foam. So you can cut things very, very fast. You can cut cubic meters of material in a matter of minutes instead of hours with the CNC. And again, it has kind of some mark. It leaves behind a trace, but you can also cut very, very precisely with this process. So we fabricated these smaller sections, and then we assemble them into submodules, and then we just piece the structure together over a few minutes. So here's a short video of the process. We had the students sitting in the small robot lab at the school, and then we had the large robot next door where we had the full-scale production happening. We had a slightly complex way of modeling it, like the workshop that we're doing at the moment. We have a much more streamlined workflow, but in principle, we were taking every piece and we were trying to find the minimal bounding box that we could cut it from. So we minimized the amount of waste material that we had, and then that waste material we recycled it by crushing it down and shipping it away. So here you can see the exploration that the students went through. They produced hundreds of samples in 1 or 2 days, and then they basically took the models that they were developing for the small robots and then scaled them up to the large robot. So because we wanted to cut large blocks of foam and we wanted to cut on all 6 sides, you sometimes run into non-trivial problems. It's like basically how do you actually reach around? So we built a small little turntable, like a manual turntable, just a sheet of plywood that could turn 90 degrees, and it was actually really, really precise. So here you can see that we had a little podium. We would put the blocks in, cut on 2 sides and turn it and cut the other 2. And the cut time for each of these pieces was, I think, 3 or 4 minutes in total. You can see it. And the assembly of these structures is also something to keep in mind, that actually we designed a system where we fabricated things in the order that they need to be positioned in. So when 3 modules are ready, we could just pop them down as the feet and then put the next one on top and start to build up the arches one by one. So they were relatively self-supporting, and then we come along and finalize them in the end. Here you can see the finished structure. After this workshop, we basically started to think a little bit about how you can go from fabricating the formwork for other material for these type of structures, and how you can go to directly fabricating freeform geometries. So working with the Technological Institute in Denmark, which are specialists in concrete engineering effectively, or like the engineering of the concrete material itself, and they're specialists that work with 3D concrete printing. We worked on a case project where we took some fiber cement facades that were going to be made, and we looked at how you can fabricate doubly curved freeform elements as a hybrid between robotic hot wire cutting and 3D concrete printing. So our approach was to basically take subsections of a doubly curved surface, and then we work with them as smaller elements. We did some environmental analysis where we could figure out what was the amount of radiation that was falling on the facade, and we tried to create elements that had a different expression to try and shade off the solar energy, depending on where they were in the structure. So here you can see an example of 3 very, very different components. One is has a lot of material and has a very steep angle, and the other ones are very, very thin. Using Rhino Grasshopper and some of the tools that we developed, we could just lay these components out, and then we could do the full simulation of the manufacturing process. And the next step for some of the research is to basically apply this robotic 3D concrete printing work that we've done with DTI, and to skip all the formwork for these shell structures and to 3D print them ourselves. We've also been talking a little bit here about if it would be possible to do them with clay, because clay has a lot of potential in terms of you can just, once you're finished with the structure, you can crush it down and you can use the material again. This is how we think that the structure might be done when it's 3D concrete printed. I think just to wrap up what I've been talking about, that in principle the approach that we took to trying to find innovative solutions to some of the problems that we encountered was in principle to kind of play a little bit. That's one of the benefits or the opportunities that we have as researchers and architects, is that we have access to this equipment, and there's no demands on having these things ready like in the morning. There's no massive budgets behind some of the projects that we're working on. So my advice would be that you can just try something out. It's likely going to fail. It failed for like a lot of the stuff that we did, but we learned to fail very fast. So we learned to try different things and to just adapt and take the knowledge over to the next process. And eventually you reach a very, very high level of precision. You can manufacture things that are you maybe thought were much more complex to do so, or much more expensive than you would have thought. As I mentioned before, we have this website, accessarch.tech. There you can find the robot control software, and slowly you'll start to find more and more tutorials. And you also find contact directly to me and the team. So if you guys are interested in exploring this field further after these workshops, feel free to contact us and tell us about your projects. Work on some things together. Thank you.